Hello, everyone. Welcome to the TAP talk for today. Today's speaker is Joana Kramer, who is visiting us from the National Labs at Los Alamos. She's here as part of the Computational Data Initiatives hosted by CK, who fortunately can't make it, so I'm giving this introduction as behalf. So Joana is an expert in all things jets. She runs simulations of jets on parsec scales. It tries to answer questions about how electrons are accelerated, how they interact with that medium, how we can observe that, and has applied it to observations as well. She did her PhD in the Max Planck Institute for Radio Astronomy in Bonn with Eduardo Ross and McDonald. And today she's going to be talking about the jets and what we can see about them. Tomorrow at 10 and on Wednesday at 10 a.m. she's going to be giving a workshop on the PLUTO code that was used for stuff. So I highly recommend, if you're interested, to sign up for that and to go and learn how to do all this yourself. So Joana, take it away.
Thank you, Boris. Thank you all for coming, and thank you for inviting me to the University of Arizona. I'm going to be talking about jets from simulations to observations, from thermal parameters to polarized emissions or non-thermal parameters. Usually, unfortunately, I can't show the YouTube video, but usually people try to zoom into galaxies. And that was the goal of the Event Horizon Telescope collaboration, to zoom into black holes, to display the shadow of a black hole for the first time. But they picked two very famous sources. So we're going to talk about on this slide about M87, Messier 87, M87 star, the supermassive black hole in the galaxy. So in 1918, the optical UV jet was discovered by Curtis. Then in 1954, the term jet was introduced with my work. In 1999, jets were found highly ordered and polarized, which is also important for my study. And the EHT, then in 2019, imaged the central massive supermassive black hole of M87. And then later on, we published the polarization of the black hole, confirming magnetic field lines and polarized and massive black holes. Thank you. Thanks. In 2023, the GMBA revealed the disk jet connection. So this three-finger image you can see here on the thumbnail of the YouTube video. So for the first time, they claimed to observe the jet launching engine. So I myself am a member of the Event Horizon Telescope collaboration. I haven't been around for the first images, but I am working on polarization on Sagittarius A star and M87 as well. So I'm going to talk today about relativistic jets and the catalogs that are out there for observations, about AGNs, active galactic nuclei, and what they are, about VLBI and how to analyze VLBI data or radio data in general. And then I'm going to talk about simulations and radio to transfer calculations. And all of this is combined by me. So thanks again for having me and giving me the opportunity to share what I learned over the last years. So let's pick one of the catalogs for AGN. So there are some catalogs to classify AGNs that have been observed. That's one of them. And then you just go into them, look what's interesting, and pick your favorite source, basically. For my study, among other things, I picked 3C84, which is a laser source, and BLUC, which is a laser source as well. Both show inclinations very close to our line of sight, but I will go into details on that. Once you pick your favorite source, you can answer some questions. The science question I had is, how does the polarized synchrotron emission in AGN jets depend on the intrinsic physics, and in particular, on the chosen magnetic field morphology? Okay, let's go into the theory behind it. What is an AGN, active galactic nuclei? It can be summarized by the unification model, which you can see basically schematically here. You have a supermassive black hole in the center, surrounded by an accretion flow. And then you have features like the jet launching in some mechanisms, Blandford and Steyr or Blandford and Payne, which are tested. You have radiative mechanisms and winds as well. You also may find a corona, and then on the disk-jet boundary, you have a relativistic jet emerging from the black hole region. If you zoom further out from the innermost center of an active galactic nuclei, you find a narrow line region and a broad line region. So it can be observed in spectra and spectral emission and classified further down into AGN types. And then you zoom further out and you find the main feature of the jet. The jet itself will then outpower the AGN system, and not only the system, but most of the times also the whole galaxy. So what an active galactic nuclei is in comparison to a normal galaxy is about 4 orders of magnitudes more luminous than normal galaxies. And of the AGN population, only about 10% are radio loud. That means they have a radio jet or radio counterpart, which we can observe. AGN can be classified by 3 properties, mainly the radio loudness, the Eddington ratio, and the inclination. And I will focus the rest of the talk, if we talk about types of AGN, on the inclination. AGN can be studied in various frequencies, basically across the whole electromagnetic spectrum, and in my case, in non-thermal synchrotron emission. But I just mentioned inclination, so we have an AGN system, and we can observe it basically from any inclination regarding the jet. So we have, for example, a radio galaxy. If we look edge on of the galaxy, if we look right into the jet, or mostly around the jet, it can be classified as a blazar type source. Why can we see emission of any inclination of any type of galaxy or AGN? That's because it's synchrotron emission, so you have electrons spiraling around magnetic field lines, emitting emission Y spiraling in any direction, losing energy basically, or giving up photons. So then for the jet itself, there are multiple features that you can observe. For example, magnetic field lines in the jet, moving features like the 2 red dots, or standing features like the blue cross, which we characterize as the recollimation shock, and in radio as the radio core in observations. A typical spectrum observed from a AGN jet is displayed or schematically shown here. You have the power over frequency and you have a tone over frequency where the system goes from optically thick to optically thin. My work is focused on the optically thin regime, so we have the latter part of the spectrum with the power law cutoff of radiative losses. And that is important because the energy distribution power law index S can be connected to the spectral index alpha in observations. So we have a powerful observational tool that we can link to a theoretical tool as well. So as I said, I'm going to focus only on the non-thermal synchrotron emission of AGN jets, not the optically thick regime, and I will also not talk about quantum scattering for higher energies than radio. Okay, let's also quickly talk about polarization. Just a recap. So polarization can be defined by the 4 Stokes parameters, I, Q, U, and V, and it's basically mathematically described by the electric vectors on the electric field plane. We then further have one very nice observational parameter as well, the electric vector position angle, which is defined by the Stokes U and Q parameter. And it is supposed to be perpendicular to the magnetic field line in the optically thin regime. So if we can observe the EVPA, we can infer the magnetic field morphology. That's basically displayed here as well, that you have a source with a given polarization. It might undergo some Faraday rotation in a medium, Faraday rotating medium. And then you have maybe a linear polarization or circular polarization. So in the circular polarization case, Stokes V, you would have a vector rotating around the electric field plane. For the Stokes Q and U linear polarization, it's going up and down or in 45 degrees. And then, that's not everything. And then I'm focusing highly on circular polarization. Why? Because it gives us insights on the magnetic field orientation as well. So not only the EVPA, but also circular polarization can test magnetic field orientations. And in principle, it can also give you insights on the jet's plasma composition. But that's mostly up to particle and cell simulations, which I am not conducting. Okay, so we talked about what an AGN is, how to pick your favorite source, stuff like that. So let's go into the history a little bit of radio astronomy. So in the last century, and in the 60s and 70s particularly, we had a single dish era in radio astronomy. So they imaged AGN jets at parsec or kiloparsec scales, and they established flux densities, spectra, AGN classifications. And then the VLBI era, very long baseline interferometry era, started, and they resolved fine jet structures and dynamics, and they discovered features like superluminal motion, so like the red knots we saw earlier in the sketch that travel throughout the jet, and they are observed at higher speeds than the speed of light as a geometrical effect, not as actually being faster than the speed of light. But that's superluminal motion. We can see precession. We can observe shocks or knots, and also the image of the black hole itself, as we now have. The cool thing about radio observations, which you, I guess, all know, is that you can actually visit the sites. So I visited some of the sites, and you can even climb into the antennas, which I would highly recommend to anyone who didn't do it yet. And you can visit VLBI sites as well, for example, in New Mexico and Socorro. But you all have a radio antenna here, so go there if you haven't been. So what is VLBI actually? That is that we have radio antennas all over the world, and we have a projected distance between a pair of telescopes that correspond to a baseline. So basically the distance between two antennae. Then the array produces a sparse sample of the Fourier domain here on the right side, sorry, as measurements. And it's filled out as the Earth rotates. Sorry. So basically we make use of the whole Earth and have a telescope as the size of the Earth, which is how we observed the supermassive black hole, MID7 star, and Sagittarius A star. So then for the very long baseline array, I just want to mention that it has the features that it has. So it has 10 antennae, each 25-meter dishes. It has a range of observable frequencies. It has a fairly high resolution, a maximum baseline of 8,000 kilometers, almost 9,000, from Mauna Kea to I think that's Hancock. And then for VLBI, if you want to increase resolution, you want to increase the number of telescopes and the distance between telescopes. But we need both small and large telescopes, because small telescopes give you a bigger beam, which is important in the UV domain, but large telescopes give you higher sensitivity and a smaller. You also want to change frequencies. So if you go from lower frequencies to higher frequencies, you can zoom in to the system. As part of the VLBA, you have the antenna here, Kid Peak. And I used the VLBA to conduct observables myself. So I had a set of 9 laser sources that I observed in 2 frequencies, 15 and 23 gigahertz in full polarization. I then analyzed the data. So I basically corrected for the parallactic angle, I fringe fitted and used opacity corrections. I solved for the group delay in polarization and leakage terms, and then I conducted prior Stokes images with the clean algorithm, which you then later used as a prior for the regularly maximum likelihood code docket. So then, now that we talked about observations, and I'm actually not going to go into details about how to reduce the data, we can move on to simulations. So just a very short introduction to that as well. Large-scale jets can be simulated with special relativistic hydrodynamics or magnetohydrodynamics. Thank you. You can simulate features like reclamation shocks, knots, the intensity or polarization. And in the post-processing, you can extract emission and the relativistic effects. On the other hand, you might have microphysics, kinetic scales, so for example, particle and cell simulations, where the hydrodynamics would be insufficient for several processes like instabilities, magnetic reconnection, things like that. But you can have a non-thermal particle hybrid approach, which I'm going to talk about later, which then can capture shock acceleration, synchrotron radiation, and polarization itself. And that's not actually really far from home. So the reclamation shocks that I'm studying can be observed already behind fighter jets or any jets in the air. So it's all just connected to plasma physics, fluids, hydrodynamics, even here on Earth. I'm using the PLUTO code, so let's quickly go through my simulation setup, and I'm going to explain more about the PLUTO code tomorrow. My jet simulations start purely thermal. The PLUTO code is an open software, which you can just download and apply several modules. One module is the Relativistic Magnetohydrodynamic module. For the magneto part of it, the magnetic field, I have three main prescriptions in my simulations: a purely polarized magnetic field where the field lines are with the jet direction, a helical magnetic field, and a purely toroidal magnetic field where the field lines are spiraling around the jet direction. For the relativistic hydrodynamic part, it's based on a conservative law, and it includes thermal parameters like the density, the pressure, the magnetic field, and the velocity. Sorry about that. I think my keynote crashed. And velocity. Oops. Oh. I use a three-dimensional grid, so all of my simulations are three-dimensional. And PLUTO uses non-dimensional units, so you only apply physical units after the simulation. So then that looks like this. We can see here a 2D slice of my 3D simulation, color-coded in density. You can see the underdense jet moving from top to bottom through a homogeneous ambient medium. You can see that we have a jet nozzle size, so we assume a pre-existing jet far away from the black hole, a couple of parsecs away from the black hole. The jet nozzle radius can vary in size. We are studying that currently. And then in the jet stream, you can see that already in the thermal parameters, we can see a feature like the recollimation shock building in the center here, with higher density than the innermost jet region itself. We can also see in the backflowing material, so the jet moves from top to bottom, and then as soon as material leaves the bow shock, it flows backwards along the jet, rolling up, basically showing these Kelvin-Helmholtz instabilities, but I haven't gotten into studying instabilities in my simulations in detail. So then, just to focus on that again, there are two very distinct magnetic field morphologies, and I studied how they would affect the polarized emission. So here's a quick example, but I'm going to go into more details, that you can definitely see a difference between those two. But I'm going to explain the main differences in a second. Let's go through my pipeline first. So as I explained, the PLUTO simulation is purely thermal. So we have a plasma density and pressure basically on the one side. And then we want to go we focus on the recollimation shock. And then we're going to go to non-thermal synchrotron emission. So we need the electron number density and the power law cutoff of the electrons. And here's basically how we do it. We have two proportionalities between the thermal parameters on the right-hand side and the electron energy distribution on the left-hand side. And then you have two integrals, and you fix the boundaries, and you solve both integrals for two unknowns: the normalization of the electron energy distribution and the power law cutoff. And then you can see again, I just want to stress it, that the power law index of the electron energy distribution is linked to the spectral index, which is a powerful observational tool between two frequencies. And then you go on and you use radiative transfer to calculate the emission. And you basically solve a matrix for the four Stokes parameters. And they are just based on the magnetic field you put in, the electron energy distribution, and then we also include Faraday rotation and Faraday conversion effects. And yet again, everything is an optically thin regime. And since my simulations are three-dimensional, we can actually rotate it. So from a radio galaxy point of view, we can now have a laser looking right into the jet itself. And since it is polarization, we can also mimic the circular polarization. Okay, so we are basically done with the theory. We talked about the simulations and the radiative transfer a little bit. However, there's one caveat. In the simulations I've shown you so far, we use a numerical trick. We basically cheat. I mean, to be fair, every simulation cheats a little bit. Everyone makes assumptions. No simulation is perfect. We make an assumption that we follow a jet tracer in the PLUTO code, which basically follows the velocity, and it is just a numerical number between 0 and 1. For the higher velocity part, you exclude the ambient medium, which is slower backflowing material. If it's 0, you have all the material included. So if you don't have a tracer, so if the numerical value is 0, you basically only see this, where the ambient medium outshines the jet. If you use the jet tracer, you highlight the jet with a velocity gradient. We have to do this because it's a thermal simulation, so there are no physical particle processes or mechanisms that would allow for the ambient medium to cool off and not outshine the jet. However, there's a non-public thing. Yeah, there's a non-public module in the PLUTO code, which is hopefully going to be public soonish, which is the Lagrangian particle module, which are macroparticles that are presenting an ensemble of actual particles, in that case electrons, and it's just following the underlying fluid stream. But besides following the underlying fluid, they develop their non-thermal attributes self-consistently. So with the Lagrangian particle module, we can incorporate subgrid physics depending on the local dynamical property of the fluid. The main part here is that we focus our attention on the synchrotron cooling, so the radiative losses, the cutoff at the end of the spectrum that we saw earlier. And as I said, the macroparticles already have a spectral distribution, So we don't have to make assumptions or proportionalities between thermal variables and non-thermal variables, because we already have the non-thermal electrons that will give you the needed attributes for the radiative transfer calculations. And just to show you that the radiative losses are actually functioning in that case, if you would choose a particle, for example, in the blue circle, which is already out of the jet stream in the backflowing material and cooled off, so it lost energy, it is slower, it lost energy. You can see a spectrum here on the right. In the spectrum, you can see from right to left earlier epochs in the simulation and later epochs in the simulation. And you can see that over time, the particle loses energy. And then you choose, then you make some assumptions about the frequency. You have the same spectrum then in frequency. You choose the frequency you want to mimic in synchrotron emission and cut off numerically every particle that is already cooled off beyond that line. And with that, we can actually go from having no jet at all to cheating to actually using particle physics to display the jet. Okay, so we're back and having covered everything basically now that we need to know for the results of my studies. So let's go into some results. Here you can see some results of the first study with the purely thermal jet and the proportionalities we made between the thermal parameters and the non-thermal attributes. From top to bottom, you can see a purely poloidal field, a helical field, and a toroidal field. From left to right, you can see Stokes I, so total intensity, linearly polarized intensity with EVPAs overplotted, so these ticks, if you can see them, and then circular polarized emission. And the main differences that I want to highlight are that first, for the poloid magnetic field, we can see a dominance by the jet spine, or the recollimation shock that we want to focus our attention to anyway. Whereas for the toroidal magnetic field, we don't see a recollimation shock, but we see an edge-brightened polarized emission. Further, we have a bimodal EVPA pattern for the toroidal case. That means on the edges of the jet, the EVPAs are perpendicular to the jet. And then in the center of the jet, they are parallel to the jet stream, which makes sense and just validates the underlying magnetic field that we put in. But it also checks with observations and now explains some observations. And then we further have two signs in circular polarization for the toroidal field. So we have a positive and a negative Stokes V. That means that resolved linear and circular polarization imaging of radio galaxies already has the potential to distinguish between underlying physics, in that case, between underlying magnetic field configurations. And since we like to rotate it to a Blazer view, we can check the same for a Blazer view. And here I just want to highlight again that we have in the Stokes B case, the circular polarization, a positive and negative sign in polarization, circular polarization for the toroidal case. So polarized emission from lasers can also hint towards a favorite intrinsic magnetic field structure. And that study was the base for my observations that I mentioned earlier with the VLBA. That means, I'm not going to repeat that, but that means from the process of reducing the data, we arrived at a set of 9 clean images for 9 laser sources that we selected based on observations in the past and that they showed high polarization in the past. From the Stokes I clean images as a prior, we went on to Docket. We performed multi-scale imaging with Docket. We used the self-calibration and closure-only approach. We made sure that the Stokes I is always greater than the linear polarization. And we didn't assume that Stokes V would converge towards 0, but that actually both the left and right-handed polarization contributes to Stokes speed. We have that in 15 and in 23 gigahertz. And with that study, we tested in linear polarization the robustness of EVPA over epochs and frequencies. So we tested it against the Mojave sample. The Mojave 2 centimeter sample is a publicly available website, and you can just choose from also many hundred sources to study your new results or probe it against it. We also did it then in circular polarization, again at 15 and 23 gigahertz. And we can see some features like we saw in my simulations. For example, a 2-sign core with a negative and positive component of the circular polarization. So with that, we did reveal a favored underlying magnetic field structure in at least 9 laser sources that we tested with the VBA. That was basically a generic study between generic simulations, just testing the underlying magnetic field. But I showed you that we can also just pick specific sources. Those 9 sources were only selected because they have high polarization, but not because they were scientifically very interesting. For me, at least. But you can actually pick any source of interest, as I mentioned earlier. So for example, if you go to Centaurus A, which is a radio galaxy, one of the closest, I think the closest radio galaxy to us, where you can go from observations here on the left with the Telemi program and the EHT to simulations on the right. So we tried, since we do see with the EHT this edge brightened feature of Centaurus A, we wanted to reproduce it with our simulations. And we more or less succeeded in that. For that, we tested various things. So we tested, let's see. Oh yeah, we went from lower frequencies to higher frequencies. So we have 1 gigahertz here, 15 gigahertz, 86 gigahertz, and 230 gigahertz. And we wanted to test the core shift and to validate that with the particle module, which is used here, we can see emission further down the jet stream and exclude cooled off particles in higher frequencies. But I just want to mention that we did manage to reproduce the edge brightening of Centaurus A. We have polarization of Centaurus A, but there are no observational polarization counterparts, so we can't confirm that yet. And then I picked 3C84. So for 3D84, another laser, even though it looks like a radio galaxy, we had an observational component here in 22 gigahertz, and in the observations in linear polarization, we saw an edge brightened polarization and bimodal pattern in the electric vector position angles. We also see a jet bending, so we try to reproduce that as well. And in that study, we chose different magnetic fields, underlying magnetic fields, and different Lorentz factors, so different speeds of the jet. In the top row, you can see different magnetic fields for a Lorentz factor of 1. So this is a toroidal magnetic field, a helical magnetic field, and topoloidal and a helical magnetic field. And then we changed the Lorentz factor for a toroidal field from 1 to 3 to 7. And we did arrive at the conclusion that the Lorentz factor of 1 and an underlying toroidal field mimics the jet the best. With a given lower speed, so like Lorentz factor of 1, the jet started to bend, and luckily it did bend in the right direction without us using any artificial wind or perturbation from the outside. And then I moved on currently to BLUC. It's one of the most famous laser sources. It's very preliminary, but we have data in the optical and in the radio of the polarization degree and the polarization angle. And we have observational components, which you can see here, which show kind of a jet wiggling precession, something like that in time. And we went on to try to reproduce that with my simulations as well. Not in time, but with inclination instead of time. So, from the observational photo on top, we try to have different jet inclinations and to mimic different jet projections, and to see how the electric vector position angle, the EVPA, would look like, how high the polarization degree is, and compare it to the observations. This is just based on the inclination. We have one tool as the plasma composition in the radiative transfer calculations, which just gives you a ratio between protons and electrons. And we can play with that, and apparently it changes something as well. And we can change the magnetic field in that study as well. So then I talked about the polarized synchrotron emission in ADN jets and the intrinsic magnetic field morphologies. We applied simulations with the various input deck. So for example, the jet knows the radius, the magnetic field, the Lorentz factor, so the speed of the jet, the distance to the jet, and the inclination. And we found a consistent spine sheath geometry with a mild relativistic flow for 3C84, for example. But between different magnetic field morphologies, we found a limb brightening in the poloidal case, which could be linked to the influence of the supermassive black hole powering the jet, so the Blatt-Wagner-Znayak jet launching mechanism. And we found a consistency of the highlighting recollimation shock region. And then we identified magnetic field configurations for radio galaxies, blazars, and also binary sources, which I didn't show today. But I am happy to talk more about X-ray binaries with you offline. Thank you so much.
All right, well, we have a lot of time for some questions. Want to ask something? Dan?
Yeah, thanks for the nice detailed talk. You said in the middle that you were doing this, you're transferring the optically thin limit. A lot of the way that we see these things, particularly at the centimeter wave stuff, depends on their being optically thick. How much does it change, the basically this conclusion, the important thing that we could learn about the magnetic field geometry from the appearance if they're optically thick?
Right, that's a good question. I wouldn't say it changes a lot, since I think just basically zoom in to the physics anyway. So it might be shielded, like the observations might be different, but the underlying physics that we saw here should be more or less the same. What the observations would give you differently, I don't know exactly. I would say the polarization would be off. It might be, I'd say higher because there's more material. Maybe lower because you see the jet less. I'm not sure about that in observations. I think for the simulations themselves and the calculations, it doesn't change a lot. But how well we could compare it to observations in that case might be more difficult.
Have you explored how the appearance changes just for the same model, but varying the frequency you're observing it?
Yeah, I mean, just varying the frequency,
Yeah, I guess so.
is basically here from very low frequencies, where you have basically all of the jet material and the ambient medium, which clouds it around. to higher precision or more structured, sharp images of the jet at higher frequencies.
Is it impossible to add the synchrotron opacity to it and just sort of make a more sophisticated radiative transfer?
I'm sure it's not impossible. I haven't looked into it, and I don't know, maybe George's code can do it, maybe GR1T can do it.
Hi, thanks for the talk. I had a question about you mentioned particle tracers and then doing a simulation where you actually follow the particles. Between the simulation where you actually follow the particles, how does their energy distribution compare to the assumptions you would make in a normal synchrotron radiative transfer? Like, are they following a power law? What kind of power law are they following, and how does it differ? Yeah.
So they follow their own intrinsic power law.
Mhm.
If you have these Lagrangian particles, whereas if you don't have the particles, we just infer from the thermal parameters to a power law distribution, but it's not as accurate. It's just more based on assumptions and the proportionality between those. But they have their own electron energy distribution. So they follow that power law distribution there.
Oh, is that fixed?
Yeah.
Oh, okay. Okay.
Yeah, you fix it. You also choose a initial power law index, a number that you think it's.
Okay. I was wondering if there's a way we could tell how good that assumption is, the power law assumption.
Yeah, it's better, but it's still not the best. But we do, so the power law index you put in as initial, as I just said, but it does evolve over the grid. So you also have now not only a fixed spectral index over the grid, but actually a changing spectral index of the whole jet.
Okay.
Since it does. Wait a second. Since it does cool. So we don't simulate the cutoff in the power law, at least, but the power law does change. So in some degree, so you do see that there's a slight change in energy, in electron energy distribution power law index over the grid.
Okay. Thank you.
There's a question on Zoom. I'll read it out loud. Aside from the sheer scale of the sizes, strengths, and the like, are there any major or unique differences in supermassive black hole jets versus stellar-sized black hole jets?
Actually, no. So I'm basically applying the same simulations currently to a binary system jet, to the jet of SS433. And I didn't change any of the setup besides the variable input deck that I mentioned, and I applied it to the SS433 system, but I didn't do anything to make a difference between this was used for an AGN or the other one is used for SS433, but we do manage to also reproduce fairly nicely the SS433 binary jet with those models.
I actually got a question of my own. You had a picture of this jet that was slightly bending, and you said luckily it bended in the right direction. Does this mean that if you were to run these simulations long enough, you could actually track how this jet bends and wobbles over time?
The precession, basically?
Yeah.
That's a good question. Yeah, I didn't run it long enough to give you a certain answer to it. I don't think it goes much higher up than that, so it might stay in that, I mean, the underlying simulation is just the same until here. It starts to bend, and I think it mostly starts to dissipate slowly in that area and doesn't go much further out, but I would have to test that.
So then are these jets unstable? Like, will they just break apart over time because of their...
Yeah, I think this one might. So if all of the other simulations in the previous slides They are all with a Lorentz factor of 7, so fairly relativistic. They are very stable, like for a very long time. I've run those for a large grid, and they don't dissipate at all. They are very, very stable, very collimated. If you go to this lower relativistic case, I don't think it will reach the end of the grid. It might dissipate before.
Yeah, sorry.
No, actually a related question. So what does the bending actually tell us then? I mean, is there a time evolution in this that you can clock with the system, or is because of the, like, what are we learning?
Yeah, so we learned in that sense that if we only had the observations, they didn't know what the jet bending caused, like if it would be an outside effect, if there would be higher density they went onto, they crashed into, if it would be precessing, if anything else is going on. What I at least can say from my simulations, which might not be 100% true, but there's no outside effect. It didn't clash into any higher density. It's the same homogeneous ambient medium that I used before, and it's in the whole computational domain. I also didn't start off with a precessing jet or a spin from the black hole. But based on this, it's really just based on the magnetic field and on the speed we chose. So that jet is slow enough to eventually start to slow down and not be collimated, not straight, but bend in some direction.
Thanks for the talk. I think I'm confused then about what the initial conditions were for this simulation.
In that case, it's the, I'm pretty sure about that. It's the purely thermal simulation with a toroidal magnetic field, underlying field. So we went from thermal parameters to non-thermal by making the proportionality assumption. Only the toroidal field, but we did test it with other magnetic fields. And then you put in the distance, the frequency, the jet speed.
So is it fair to say you're constructing a stable jet and then seeing what you would observe, as opposed to trying to have it form and then evolve?
Yes.
I have a follow-up question. So is the magnetic field fixed throughout the duration of your simulation, or do you allow it to evolve?
It evolves with the jet, but it's fairly fixed.
Okay.
So, I mean, it doesn't do much. So it starts off at the jet nozzle.
Mhm.
There's no magnetic field on the domain before the jet starts. And then with the jet, it's only in the jet. So there's a magnetization radius. I chose that the magnetic field would be only within half of the jet nozzle radius. So only in the innermost jet part. And then as the jet evolves, it carries the magnetic field with it. And it's, as you see here, for example, for the polar case, it's very stable in the polar case. For the toroidal case, it's also pretty stable. I mean, it looks disordered. I mean, it is disordered, but if you do rotate it and analyze it enough, it's very much the same throughout the whole computation. Very stable in that sense.
So from the comparison you showed to the data, it seemed like a lot of them, the toroidal magnetic field, is that the story for all these AGN that they seem to have a toroidal magnetic field? Any not do that?
Good question. I think we just by chance picked. I mean, I had the simulations basically first, and then went to simulations, to observations of sources of interest. And since I did see the edge brightening, and I think that's a very distinct feature to see, I just displayed most sources that show that kind, like Centaurus A, since it does show the edge brightening. I was like, hey, I do see that in my simulation, so let's try to reproduce it. And indeed, the toroidal magnetic field does reproduce it. The same for 3C87, since we do see at least in linear polarization the edge brightening. So I tested, and it does show that the toroidal field mimics it the best again. Currently for SS433, we are kind of puzzled because the poloidal field, in that case, the poloidal magnetic field reproduces the observations the best, because we do see this in X-ray, the standing feature where the jet starts to evolve from SS433. And the poloidal case in my simulations has the standing feature as well. So it mimics that the best. However, the jet power is way too high in our simulations compared to the observations. So we do think there has to be some toroidal component and not a fully poloidal case. So right now we are testing intermediate steps between toroidal and poloidal. Not just one, as here, like the helical cases I tested before, I think are equally toroidal and poloidal. But right now I'm going on the spectrum between toroidal and poloidal to see how far I can go to still reproduce the standing feature, the reclamation shock. On the other hand, have the right power, but also see observational pattern that polarization pattern that mimics the simulations in that case. So it's not always the toroidal case.
But in this case, just to follow on,
Yeah.
can it be a scale, a factor that it's a scale that is involved, that these jets are much larger scale than S443? Relatively speaking, of
Right.
course, yeah.
Yeah. I mean, they're less powerful, so maybe yes. I mean, galactic sources or SS binary jets are less powerful than AGN jets. So that might be true, but I think we just have to find the right simulation configuration. And as I said earlier in the beginning, the PLUTO simulation is non-dimensional, so that's, in my view, applicable to either system. And then you just have to find the right normalization, so the right physical units you apply to it, which we are looking into right now for SS450.
I have another question. I noticed with a lot of the comparisons you've done, which are really cool, but I've noticed that the inclination angle is not well constrained. Can you constrain the inclination angle, and is it degenerate with any of the other parameters you're tuning?
Yeah, I think I can at least give a more accurate range than observations, not the precise angle, but definitely break it down to some smaller range. What was the latter part of the question?
Is the inclination angle like degenerate with the magnetic field structure or like the gamma factor that you're seeing?
No.
All right, well, thank you, Joana. Let's thank the speaker.